So that Hankel representation of the gamma function leads us to our starting point, which is asymptotics on what's called the standard function scale. And we'll just do the leading term throughout most of this lecture the way we've been doing, but all of these theorems can be taken to any asymptotic precision. And so it's a very simple theorem that is actually useful to apply in lots of instances. So if you have any real alpha, actually any complex alpha, as long as it's not zero or a negative integer, then you can get an approximation to the coefficient of z to the n in 1 over 1 minus z to the alpha. And that is exactly n to the alpha minus 1 over gamma of alpha. So we'll look at the proof in the next couple of slides, but this is the kind of scale that we're looking at. Let's go up by a square root at a time. So we know 1 over 1 minus z, coefficient of z to the n is 1, and 1 over 1 minus z squared, the coefficient of z to the n is n plus 1, and cubed is n squared, and so forth. So going down this way, we add a power of n, and so what this table is going to show is what happens with the square roots. So if we take alpha equals 1/2, we know gamma of 1/2 equals square root of pi. We get n to the minus 1/2. So it says the coefficient of z to the n in 1 over square root of 1 minus z is 1 over square root of pi n. Now if we take alpha equals minus 1/2, then we get n to the minus 3/2, and then we now have gamma minus 1/2, which is an extra 2. So its coefficient of z to the n in square root of 1 minus z is asymptotic to minus 1 over 2 square root of pi n cubed. That's what the formula tells us. So now, when down here we're going up by a factor of n every time we jumped 1 in the exponent, same way, factor of n. So now another factor of n, so now it's square root of n to the 5th, and then a slightly different constant depending on properties of the gamma function. And then going the other way, it was 1 over square root of n, now it's square root of n, again with a slightly different constant. So except for the negative integers, where the negative integers, it doesn't make much sense to talk about a coefficient of z to the n and 1 minus z, because most of them are 0. So negative integers have to be an exception, but everywhere else we have these things are analytic, and we have the theorem gives us on any function in this standard scale, any alpha, it'll give us an approximation of the coefficients. So that's very powerful and very useful. And again, the proof of the theorem extends to give a full asymptotic expansion in decreasing powers of n with that leading term, n to the alpha minus 1 over gamma of alpha. So it's a very generally applicable and powerful theorem. So for example, with this theorem, we can take our generating function for the Catalan numbers and immediately know from the theorem, the asymptotic expansion that we derived with so much pain using Stirling's approximation of binomial coefficients and other things. It's an immediate transfer theorem from the standard scale out to the asymptotics of the coefficients that we can apply broadly. Now, I'm not going to go through the full proof. Remember, I acknowledged that we're entering deep water. This one's not too bad. The key concept in the proof is to figure out, remember the square root function, and the way that it goes was a negative integer, but we take 1 minus, so it's in the positive. There's going to be this area where there's going to be a line or a slit where the function is not analytic, where all the essential singularities are. And what the proof does is define a contour of integration that ignores that. And all we need to do is be sure that inside that contour of integration we have an analytic function. And we know that there's these areas where it's not analytic, and we don't think too much about what's outside, but that's the setup. Is that we want to define a contour of this type called Hankel contour. We make the slit width 1 over n to get the asymptotics to work out. So the sketch of the theorem is to get the coefficient of z to the n in 1 minus z to the minus alpha, we use Cauchy's coefficient theorem. It says the coefficient of z to the n in a function is 1 over 2 pi I integral over a small circle where it's analytic, which the origin is fine, times dz over z to the n plus 1. That's the basic Cauchy coefficient formula. And then what we'll do is change variable to z equals 1 plus t over n in that formula. So then if we make that change of variable, then an n to the minus alpha comes out, and a minus t to the minus alpha stays in. The z to the n plus 1 becomes that 1 plus t over n to the minus n minus 1. So there's a little algebra there with that change of variable. But that pulls out the n to the alpha minus 1 term that we're looking at. And then we take our contour of integration, and through the null integral property, we can deform it any way we want as long as we don't go over a pole. And so we deform it into a Hankel contour. And then take r to infinity, which leaves us with a slit like the one in the Hankel representation of the gamma function. And indeed, what we do is this integrand is just like the one in Hankel's formula for the gamma function, and that gives us the gamma of alpha. Now, this is just a sketch of the proof, and there's a lot of details to check in this proof. But you can do that with some time studying the book, depending on your mathematical level of mathematical sophistication, and easily follow this proof. It's a standard proof in complex analysis to establish the standard function scale. It comes right from Hankel's formula for the gamma function. But otherwise, if you're interested in just applications of analytic combinatorics, it's an excellent transfer theorem to know. If you have the third root of 1 over 1 minus z, or whatever alpha that you have asymptotics in terms of the gamma function. And then it's just a matter of computing values of the gamma function. And in a great many cases, it's alpha equals 1/2, as we'll see. Because of properties of the way that we construct combinatorial classes, the generating function equations that we get have constraints that lead to this gamma of 1/2, exactly as in this theorem. So that's a very broadly useful function that can be used in many applications. And actually, we can extend it to include logarithmic factors. So if we add a factor of 1 over z log 1 over 1 minus z to the beta, then it brings out a log n to the beta term. And I'm definitely going to skip that proof in lecture, but it's a straightforward extension of the previous proof. Once you get the previous proof, you can get this one. And again, knowing this theorem, say in the very first lecture for analysis of algorithms, when we analyze quicksort, we can immediately get 1 over 1 minus z log 1 over 1 minus z equals log n. Or 1 over 1 minus z squared log 1 over 1 minus z equals n log n. This transfer theorem gives us the coefficient asymptotics immediately for lots of generating functions that arise in practice. And again, so that's another one. And then there's a table in the book that actually does it for all the alphas and betas, for alpha and 1/2, just like on the table that I showed. But that's a very powerful and useful transfer theorem. So, as I mentioned, the promise of analytic combinatorics allows us to work at a high level with constructions immediately giving generating function equations by the symbolic method, and then a transfer theorem that takes those generating function equations right to coefficient asymptotics. Same for, we looked at cycles and permutations in the earlier lecture and came up with the generating function 1 over 1 minus z log 1 over 1 minus z. Knowing the standard function scale, we can immediately take that to get the coefficient asymptotics log n. No computation needed at all. So general transfer theorem that's useful in lots of applications. Now these two examples, well particularly this one, elementary, and there's many ways to get these kinds of results. Again, as usual, when we look at variance and we look at more complicated things, we can still use the same transfer theorem to quickly get the result without any calculation, very little calculation. And we'll see many, many examples of that in the next lecture. That's the standard function scale, which is our starting point for singularity analysis.